confidence interval for difference in proportions. We're given two proportions, okay? And so I'll explain why we're doing that here. Professor Borbely describes research on the sleep laboratory. During normal sleep, the phase known as REM occurs every 90 minutes or so. It's thought to dreams occur during the REM phase. Using electronic equipment, the sleep laboratory is possible to detect the REM phase in a sleeping person. If they're awakened immediately after the REM phase, they're usually can describe the dream that just taken place. Based on a study of over 600 people in the Zurich Sleep Laboratory, has found that one-third of them dream reports contain feelings of fear, anxiety, or aggression. There's a conjecture that if a person's in good mood when going to sleep, the proportion of bad dreams might be reduced. Suppose we have two groups of subjects randomly chosen for a sleep study. In group one, before going to sleep, the subject spent an hour watching a comedy movie, and there's 175 people, in which 49 had dreams of fear, anxiety, or aggression. In group two, they did not watch a comedy movie, simply went to sleep, and they had 180 people. 63 had dreams with feelings of anxiety, fear, or aggression. Why could groups 1 and 2 be considered independent binomial distributions? So, well, we have basically their independent random samples here, and they're independent random samples, and they each with each receiving a different treatment. So, like one watched a comedy movie, one went to straight to sleep. Okay, so independent random samples, each different treatment. Is the large sample satisfied? Well, we have to have at least 5 in each group. So we have to have at least 5. So like in the first set, we have 175 people total. 49 had dreams of it. So we had 49 that had dreams of basically I'll call it bad dreams, and we had at least 5 that with bad dreams. We had 49, and we also had at least 5 without bad dreams. On the next one, we had at least 5 with bad dreams. We had 63, and then there's also at least 5 that did not have bad dreams. So on this one, we both of them are satisfied here. So we're good. So we have it n times. So basically, you don't have to worry about writing this down, but n1 times p hat 1 is greater than 5. n1 times p hat, or a1 times, I guess you can call it q1, q hat 1 is greater than 5. n2 times p hat 2 is greater than 5, and n2 times q hat 2. And let me just say, what does this mean? We had at least 5 people that had bad dreams in each group. We had at least 5 people that did not have bad dreams in each group. That's what that means. So it's a large enough sample. Now, how do you do a 95% confidence interval? It's proportions, 2 sample proportions, because we have 2 separate samples and we're doing proportions. So 49 of 175 had bad dreams. So how can you do this in the calculator? You go to stats, test, 2 prop z int. So stats, test, 2 prop z int. X1 is the number in your first group. It's like your R1, the number in your first group that had bad dreams. It's to be 49. N1 is your sample size in your first group, 175. Salt will do this for you. X2 is the number that had bad dreams in the second group, so that's 63. And then N2 is the total from the second sample, 180. And then the C level is 0.95. And then calculate. Okay, so there's your confidence interval, negative 0.663 and 0.02634. Okay, so okay, I interpret this. We are 95% confident that you can make these percentages that the interval between, I'm going to make these percentages between negative 16.63% and 2.63% contains the percentage difference of bad dreams between group 1 and group 2. Okay. So what you would be looking for here is it if it's no difference, then like zeros in the interval. So there's zeros in this interval, so there doesn't appear to be a significant difference between the bad dreams of watching a comedy movie versus just going straight to sleep. Okay, if it was like one way or the other, there would be a difference there. So that's all you really need to know there. How do you do this by hand? You do not need to know how to do this, but I need to find the margin of error. It's a Z procedure. This is a Z procedure. Proportions are Z. So Z of C for 95% is 1.96 times P1 hat. Now, P1 hat is the proportion of per 1. So you do not need to know how to do this. So P1 hat would be 49 divided by 175.28 times Q1 hat, which is 1 minus P1, so be 0.72, over N1, which my first sample size 175. My next one's P2 hat would be the proportion from the second sample, so 63 divided by 180.35. Q2 is the complement of that, so it'd be 0.1 minus 0.35, 0.65 divided by 180. And so 1.96 times the square root of 0.28 times 0.72 divided by 175 plus 0.35 times 0.65 divided by 180, 0.096. Then I would find the difference in proportions. The difference in proportions would be 0.28 minus 0.35, negative 0.07. So negative 0.07 plus or minus 0.096, which is negative 0.07 minus 0.096, negative 1.66. So you see that's the same thing I got. And then negative 0.07 plus 0.096 would be 0.026. Okay, so that's how you do it by hand. But as I said, you don't need to know that. You could just do it in the calculator or do it in Solve.